Okay, so now we're gonna just prove a rule for calculating the derivative of of the inverse of a function, and this is sort of not strictly related to the mean value theorem itself. Um, so I'm not actually entirely sure why they sort of shoehorned this uh, formula into this section, but I don't know, whatever. It's useful, so it'll be good for us to go over now. Right, so to sort of motivate this, what they do in the book is they use the chain rule to kind of give like an informal proof of what the formula should be. But I think it's nicer just to kind of draw a picture and see, because there's a simple relationship between f and its inverse graphically, right? So let's say like here's A, here's B, and f is like something like that. I don't know, right? So this is f of x. Okay, then let's see. This is supposed to be a line of slope 1. So the graph of the inverse of f, you can always obtain by just reflecting the graph of f across the line y equals x. So this is y equals x. The line, quote unquote, y equals x. I mean, whatever that means. And so let's see. So you'd get something like this. I don't know. And then like something like that, right? So then this is the graph of f inverse of x. Okay. And of course, we're talking about compositional inverses. So f inverse is the compositional inverse, not 1 over f of x. Okay. Which is, of course, 1 over f of x is just like the multiplicative inverse, and that's not what we're talking about at all. Right? So because the whole point is that like the compositional inverse in the graph, all that happens is you just switch which value of each, like at each point on the graph, you just switch which one is y and which one is x, right? And the result of doing that is reflecting the graph across this line y equals x. Okay, so then if you had like a a tangent line or something, right? That reflects in this picture to become a tangent line on the graph of f inverse of x at a different, obviously the actual x value of this point changes because it changes to whatever y point you were looking at. But the slope of the line, so if this is slope m, when you reflect a line like this across this line y equals x, the resulting slope is always 1 over m. So piecing this all together, the formula we expect would be that f inverse prime at y equals 1 over f prime of x, where y equals f of x. Okay? Because as you can see, right, if this is like, if this is, so this is x, then this is f of x. So that means this is f of x as well, right? So, and then of course, this is x but that doesn't really matter, right? So, but this is f of x and this is x, and so you can see the slopes at these 2 points are related by this reciprocal relationship. Okay, so that's the formula we're going to try to prove. So let's state this as a theorem. So 29.9 theorem. So let f be a 1, 2, 1 function on an interval I. And again, we're not really specifying whether I is, open or closed or half open or half closed. It could be any of those things. And set J to be f of I, another interval. Right, we actually proved this before. In fact, we proved that if f is a one-to-one function on the interval I, then f has to either be strictly increasing or strictly decreasing. But at any rate, in either case, the set of values of f form another interval. So then if we set J to be this, then f inverse, we can actually define an inverse for f whose domain is J, right? Because f becomes surjective onto the set J. So then, let's say, sorry, so f should also be differentiable. Or yeah. So one-to-one continuous function. If f is differentiable at x naught and f prime of x naught is not equal to 0, of course, this picture, if f prime was 0, then in the reflected version it would be like a vertical tangent, which then obviously it's not differentiable there because the limit is infinity or something. So yeah, f prime is not 0, then f inverse is differentiable at y naught, which is f of x naught, and f inverse prime y naught equals 1 over f prime of x naught. Okay. All right. So proof. Oh, right. Oh, sorry. I is actually assumed to be open. Okay. Oops. It's actually kind of important. So note that J is also open. This is one way to see this would be that f is 1, 2, 1 means that f is strictly increasing or strictly decreasing. Right, and if you think about a strictly increasing function on an open interval, the image of that also has to be open because the minimum would be at like the left endpoint, but the left endpoint isn't included in the open interval, so the minimum value also isn't included, in the image. And the same thing goes for like the maximum value or the supremum, and it's like supremum and infimum if you want. So the sup and the inf of the values are not included, so it's actually an open interval. So, right. We are assuming that f of x, so the limit as x goes to x naught of f of x minus f of x naught over x minus x naught equals f prime of x naught. Right. and f prime of x naught is not 0. So by theorem 20.4, which is just one of the basic theorems about, adding, multiplying, and dividing limits, this tells us that the limit of 1 over this, which is x minus x naught over f of x minus f of x naught, equals 1 over f prime of x naught. Okay? So let epsilon be greater than 0. What we're going to do is show that, first of all, set whatever. So set g to be the function f inverse, just for convenience, I guess. We want to show that there exists a delta such that for all y with absolute value of y minus y naught less than delta, we have that the absolute value of g of y minus g of y naught over y minus y naught minus 1 over f prime of x naught is less than epsilon. Okay. So so what we end up having is we end up calling this eta. Okay. So let's just call this eta instead. Okay. So this would show that g is differentiable at y naught and that the value is 1 over f prime of x naught, right? So the point is that we can recognize this as this expression here as so g of y is like some x minus and then g of y naught is x naught over f of x minus f of x naught, right? Right. Sorry. So I just had to double check something in the notes, but so we can recognize this as x minus x naught over f of x minus f of x naught for some value x, right? The question is like, how close is x to x naught, right? By forcing x to be close to x naught, right? Like we said here, so this limit, the limit of x minus x naught over f of x minus f of x naught is 1 over f prime of x naught. So by forcing x to be close to x naught, we can force this difference to be small, right? By forcing x to be close to x naught. But we only have control over y. But the thing about g is that it's continuous, right? So by controlling y and making y be close to y naught, we can make g of y be close to g of y naught, which is the same thing as making x be close to x naught, right? So so the point is, first let's figure out how close we need x to be to x naught to make this difference be less than epsilon. So choose delta such that for all x in I with x minus x naught less than delta, we have absolute value of x minus x naught over f of x minus f of x naught minus 1 over f prime of x naught is less than epsilon. Okay, we can do this because we showed, like we said, we know this limit as x approaches x naught is 1 over f prime of x naught. So that's possible. Okay, so we can choose this delta. So we chose delta greater than 0. Now the point is that since we have since g is continuous, we can control x minus x naught effectively, which is the same, aka g of y minus g of y naught, by controlling y minus y naught. So then since G is continuous, there exists an eta greater than 0 such that for all y in J with y minus y naught less than eta, we have G of y minus G of y naught is less than delta. Okay? But then for these values of y, we see that G of y minus G of y naught over y minus y naught minus 1 over f prime of x naught is less than epsilon because G of y equals x for some x in I with x minus x naught, x minus x naught less than delta, and G of y naught equals x naught, right? So the fact that G of y is just some number that is within delta away from x naught, right? So the point is that the way we chose delta ensures that whenever we have a number within delta of x naught, then this expression, right? Well, this expression over here, this expression is less than epsilon whenever x is within x naught, or within delta of x naught. So here it's like G of y naught is x naught, and then G of y is just some number within delta of x naught. So this is definitely less than epsilon, right? The point is this is equal to x minus x naught over f of x minus f of x naught sum x with x minus x naught less than delta. Okay, so that's the formula for differentiating inverses. Let's just look at one quick example of this. So say right, f of x is x to the n on 0 infinity, and so G of x is, or G of y, let's keep it straight. So G of y is y to the 1 over n, right? Where we conventionally take the positive nth root, right? So okay, well they do it. Let's just stick to the positive. I mean, so they talk about the case where the domain here can be all of R if n is odd, but I'm just gonna like not deal with that right now. So right. So say y naught is in 0 infinity. Then the theorem tells us that g prime of y naught is 1 over f prime of x naught, where x naught, or sorry, where f of x naught equals y naught, right? So i.e. in this case, if f of x naught equals y naught, x naught to the n equals y naught. So y naught equals 1 over n. Sorry, not 1 over n. X naught to the 1 over n. Right? Or sorry. X naught equals y naught to the 1 over n. And f prime of x in general is just, as we've seen, nx to the n minus 1. So g prime of y naught is 1 over n y naught. Yeah, y naught to the 1 over n to the n minus 1, right? So this is 1 over n y naught to the 1 over n minus 1. So that, yeah, if you just do the algebra, right, you'll because down here you have n minus 1 over n. So then to, reciprocate, or not reciprocate it, but to move it out of the denominator, you'd get negative n minus 1 over n, which would be 1 minus n over n. And then you can separate that to get 1 minus n over 1. So anyway, yeah, this way we can, so this proves the formula for differentiating the nth root. And it's the same power rule as we're normally used to. But technically speaking, we didn't prove the power. We only proved the power rule for like positive integer coefficients and maybe negative ones, but just at least integer coefficients. So now we can do it for, arbitrary rational, not coefficients, exponents. So we can do the power rule for arbitrary rational exponents now. Anyway, yep, that's all for this lecture. See you in the next one.